Okay, there's one more concept I want to talk about with binary trees before we move on to binary search trees. And that's the concept of level and depth. So we can assign a level to each node by recording how many steps it takes to get from the root to that node. So 10 is at level 1, 7 and 15 are at level 2, 3, 9, 12, and 20 are at level 3, 8 and 14 are at level 4, and 13 is at level 5. So the level of a node is the number of steps in a path, and the shortest path from the root to that node. So 13 is level 5 because I go 10, 15, 20, 14, 13. That's 5 steps. 9 is at level 3 because I go 10, 7, 9. Okay, so that's the level. And all the nodes at a particular level, if I draw this tree this way, they're kind of parallel to each other. You see that? So they're along this horizontal line here. Okay, then I can define the depth of a tree as the maximum level of any node, or overall nodes. So in this example, the depth is 5. So what I'd like to do now is write some code, a recursive function to compute the depth, and I will have you complete a recursive function to print all the nodes out at a particular level. Okay, so let's make a function. I'll call it int get depth. It'll take in a tree. And this is often the way recursive functions work in C++ and Java. I should define an overloaded version of this, which takes a node, because I'm going to be doing this recursively on subtrees. So this is called tree node, and depth is going to be how far down I am when I get to the subtree. So what I'll say is, okay, if the root happens to not be null, so if there's actually something in the tree, then I will call this get depth on the root to kick it off. And the depth at the root is 1, right? So 10, here's the root, it has a depth of 1. So that's the first depth. Okay. So now we need to figure out, well, is there more to it? And we'll do that recursively. So maybe there's not more to it. Maybe, we stop at this node. But what we should do is we'll check to see if the left subtree is not null. If the left node is not null there, then we have to do some recursion. So what we'll say is, so I'll make a variable left. Yeah, let me actually do it this way. Okay, so if the left node is not null, then I actually have to do some recursion. So I say left equals get depth node left depth plus 1. Because when I go down and visit this node, I'm going down another level. Okay, so my path has length plus 1 to what it was before. Okay, and then a similar thing for the right node. So if the right node is not null, then we need to do the recursion off to the right. And we're also going down another level. So what we'll say is, we'll assume that the depth is the depth of the left subtree, but if the right subtree happens to have a depth that's greater than the left subtree, then we'll set it to be the right subtree's depth. And that's all there is to it. Okay, so stare at this for a second. What I'm saying is, okay, I'm calling depth on a node that's not null. And this is how deep that node is so far. I want to keep going and see if I can go deeper on the left or the right. If the left actually exists and is not null, then I'll go down to the left node 1 deeper and report the depth there. if the right node is also existing, then I can go down a depth of 1 off to the right and see what it is. And the depth of the whole tree from this node on is going to be the maximum between the right and the left depth. So here I see, if I start at the root, the right is deeper than the left. So the left should return 4 here and the right would return 5. So in this case, this if statement would be true and we would return 5. So that's the way the recursion works. Okay. Now let's just make sure this actually runs. So this should output 5 on this example tree. So let me compile it. Let's bring this over here. And we get 5. Beautiful. Okay, there's my 5. Just to show you, if I, let's say on the right subtree, I add a node to the right of 13. So let's say, well, I've actually run out of values here. It turns out 12, 13, 14 for the Inorder. I guess it can have a tie. I'll add a node 13 to the left of 13. Okay. So what I'm concerned about making sure that, if I trace my pencil around and do an Inorder, it goes 3, 7, 8, 9, 10, 12, 13, 14, 15, 20. Okay, anyway. So the thing to the left here is supposed to be less, I guess we can say less than or equal to. Anyway, so this should have a depth of 6 now if I add another one of those. So I'll say node, left, right, left, left. So I'm just adding another node here. Equals new tree node 13. Okay, so now I should be seeing a depth of 6. Good. Okay, so this seems to be working. Now what I'd like you to do next is to finish writing a function that will print out all the nodes at a particular level. And what this is really just a truncated Inorder traversal. So you can start with the Inorder method. You just have to modify it a little bit. So I'll say void, I'll call this print level. So I'm going to pass along a binary tree, and I'm also going to pass along a level that I want to print. Okay, and then there's going to be another overloaded version of this, which will take as an argument a node, and it will also take the level that we're shooting for, but also the current level that we're at. Okay. So yeah, I just need to update these. So I'm saying print level node left. This was some other stuff I had before. I can ignore that. Yeah, so normally what you do in Inorder is at this point you'll then print the node's value, and then you will call Inorder again. So here, let's see, we've got 3 parameters. We've got the node. We have the current level that we're on. So if we go to the left, we're going, just like with the depth, we're going down a level. The level is increasing by 1. We still have the same level that we're shooting for. Then we print the value. So this is really just an Inorder traversal so far, but I'm keeping track of the level that I'm at. So it's looking like a mix of the Inorder and the depth thing I did a moment ago. Okay, so to kick this off, I will say Inorder starting at the root at a level of 1, and then we're shooting for this level. Now this right now should just print out all the nodes in order. Let's check. So I'll just say print level t. I put a 3 there saying I wanted to print level 3, but that's not actually going to happen yet. You have to make that happen. Let's see, no matching function call. I meant to say not in order, I meant to say print level. Okay, there we go. Okay, so this actually just prints out everything in order. 3, 7, 8, 9, 10, 12, 13, 13, 14, 15, 20. But I want you, in this example, I'm saying print out level 3. You should print out 3, 9, 12, 20 in that order. So I want you to print the level out from left to right. And so all you have to do, this is mostly done. You just don't want to continue the recursion if you're already at the level. So you just stop the recursion. And you also only want to print if your current level is the level you're shooting for. So that's how you do it. So do that real quick, and that's the only exercise. And then tomorrow we'll do more with trees in class. Okay.